Okay, so here we go. We're going to move on into, we're going to finish off Chapter 2. And work through Chapter 3. Okay. So let's just recap what we did last week. Last week we were introduced to data. We talked about populations and samples, observational studies, and experiments. We also covered the difference between numeric versus categorical data. And we looked at summaries for categorical data, as well as graphic displays for categorical data. So what do we call the table that we use to summarize categorical data? The table that we use to summarize categorical data, what is that called? It's a frequency table. I'm pretty sure that's what I heard. Frequency table to summarize categorical data, and then to the graphic display, that is the bar chart. Okay. All right, let's just a quick check, see if you remember. I'm going to show you two bar charts. Okay, and we'll say this is, we'll just keep it like that. All right, so I'm going to call this one bar chart A, bar chart B. Don't shout out your answer, don't shout it out. But which bar chart shows more variation in the data? Don't shout it out. Okay, so we're looking at a categorical variable, either M or F. And we've got bar chart A for one set of data, bar chart B for another set of data. Okay, so now go ahead and say which chart has more variation in the data? B. B. Okay, great. That's in unison. Very good. We could start a choir here. All right, let's see. 01, and we are April 7th, Stats 10. Great. Okay. Well, that's good. So let's continue on, and now we're going to talk about graphic displays. For numeric data. Okay, what are some examples of numeric variables that we can use for numeric data here? Okay, so one example of a numeric variable is age. What else do we have? Height. Okay, so if we're dealing with people, we can deal with people's ages, people's heights. These are numeric variables. They tell us how much or how many. Okay, so again, that is the key. A numeric variable tells us how much or how many. Okay, so let's just say, or let's say we have another one, number of siblings. Okay, that would also be a numeric variable. It tells us how many siblings a person has. And so let's just say we went around the classroom, and we're not actually going to do this, but we'll say we record the number of siblings someone has. So we've got person, so we have, you know, Adam and Betty and Cindy and, I don't know, Doug, etc., etc., etc. That's Doe. All right, so let's just say Adam has, you know, 1 sibling, Betty has 2, Cindy has none, Doug has 3, and let's just say this is what we've got. Okay, so and you can imagine more and more data points gathered, but let's say we looked at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is the responses from 14 people. Okay, and we can imagine, you know, if we were to do this whole classroom, we would have, you know, 70 something or almost 80 responses. But I don't feel like asking every single one of you, and probably not all of you would want to tell me, and, you know, we'd have to define what exactly is a sibling, you know, because some of your parents might have gotten separated and remarried, and then now you've got this blended family, and yeah, oh, whatever. Okay, so let's just say this is what we have, and we're going to create summaries and graphic displays. Okay, so we could create a frequency table. This is allowed. Okay, and over here, what we would have is we would have the value that we take on and the frequency. So let's count. One possible value is 0, and how often, or what is the frequency that 0 showed up in our 14 responses? 2, right? We've got 2 people with 0 siblings, Cindy and someone else, so I'm going to write a 2 right there. And let's see, how many times did the number 1 show up? 1, 2, 3, 4, 5, okay. And let's look at the number 2. How often did 2 show up? 3 times. I'm going to run out of colors here. That's all right. Okay, and then we got 3, 4, and 5. How many times did 3 show up? Twice. How many times did 4 show up? Once, and 5 also showed up once, okay? And so we also have a total of, this should add up to 14. 1, 2, 3, 4, 7, and 7, yeah, 14. Okay, 14 total. Okay, so this is a frequency table. So we have a few ways to display our data, okay? One is with a dot plot. Now, the key thing is that for all graphic displays of numeric data, you're going to have a number line somewhere in the graphic display, okay? So all graphic displays for numeric data will have a number line. Okay, so let's make a dot plot. And we're going to draw a number line. And the number line has to cover the values that we observe. So we observe values between 0 and 5. So I'm going to just draw tick marks for 1, 2, 3, 4, 5, and for good measure I will continue it. And with a dot plot, we go through and we put dots for every single value. Now we can create a dot plot based on the frequency table, or we can create a dot plot from the raw data itself. Okay? Now if I do it from the raw data itself, I would start off, I would look at the first data point and I would see a 1, and I would draw a dot at 1. And then I would see the next data point is a 2, and I draw a dot at 2. And I keep going, and the third data point is a 0, and I draw a dot at 0, and I just continue drawing dots. And when I see this one repeat, I draw another one right there. And then I see a 2, and I just stack up the dots. Okay. And so there my dot plot ends up looking like that. And we can see that our dot plot also matches our frequency table. We can see that for 0 there are 2 dots. For the number 1 there are 5 dots. For the number 2 there's 3, and so on and so forth. Thus our dot plot matches our frequency table. Okay. Construction of the dot plot okay with everyone? Everyone's good with that? Okay. So it should be noted that you should try to make sure all of your dots are about the same size, and when you stack them they take up about the same amount of vertical space, just so that, you know, 2 stacks that have 2 dots in it should be the same height there. Okay. So this is a dot plot. We can also create a histogram, which is very similar, except instead of drawing dots, we draw bars of that height. So a histogram is going to have a number line across the bottom. So actually I'm going to just copy this number line because I'm quite pleased with myself here. Okay, so this will serve as our number line for the histogram as well, but this time we're going to have a vertical axis to indicate the height. Okay, so I got, 1, 2, 3, 4, 5. So I just go 1, 2, 3. So the height of the bar now indicates the frequency. Okay. Now, when we draw a bar for the histogram, the bar that represents the value of 0 starts at the left edge of 0 and goes up to 1. So the bar for 0 should be 2 units high, and it starts, the left side of the bar is at 0 and it goes over to 1. The bar for 1 is 5 units high, and its left edge starts at 1 and it goes up to the 5. And it goes like that. The 2 is 3 units high. And it looks like that. The 3 is only 2 units high. And lastly, 4 and 5 each are 1 unit high. Okay. Okay, and so now we have a histogram that looks like this. Okay. Is the construction of the histogram okay with everyone? All right. It's very similar to the dot plot, except you're drawing bars instead. Now, be sure that we call this a histogram and not a bar chart. A bar chart is for categorical data. A histogram is for numeric data. Okay? So histograms are for numeric data. Dot plots are also for numeric data. So everything that we've seen here is for numeric data. With histograms, you can get fancy and you can color in these things if you want, but we don't have to do that. Okay. Is that okay? Yes, question?
4 and 5 have one frequency? Or?
Yes. Okay, so with the histogram, you're going to want to create the frequency table first. Okay, so you create the frequency table first, and then you can draw the bars of the appropriate size. Yes, another question.
What's the other table called?
This one over here?
Dot plot.
this is just your data table, okay? Each column represents a variable. Each row represents what? A case or a subject, okay? So in this case, we've got, or in this data table, we have 14 rows, one for each case or one for each person, and the column is the variable that we're looking at, which is the number of siblings someone might have.
Would it be wrong to call that one a frequency table also?
Yeah, this is not a frequency table. Do not call this a frequency table. This is just your data table. This is your frequency table. Frequency tables are to summarize the data tables. Data tables are just raw data entries. We don't try to, we just leave that as is. We can create summaries with frequency tables. And the graphic displays are just ways to display what we also see in a frequency table, or a way to summarize it. All right, is that okay so far? Okay, let me show you that with histograms, we can also create binned histograms. So if I go back, let me just copy this data table. Now, this is not going to be the best example because we probably wouldn't normally do this. But if for some reason we wanted to create binned histograms, I'm going to just demonstrate how we would do that, okay? So we can also create a binned, like garbage bins, okay? Binned frequency table and histogram. So this is more useful if you've got lots of data and maybe too many bars, okay? So we would create a bin, and the bin can be any size you want as long as they're all the same size. So I'm going to create a bin, and it's going to go from 0 to 1.99, okay? And again, this is the number of siblings, so we're never going to have 1.99 siblings. When I say 0 to 1.99, it's really just 0 to 1, right? Okay, and then the next bin will go from what? 2 to 3.99. Okay, and really, because we don't have fractions of siblings, it's just really 2 to 3. And then the last bin will go from 4 to 5.99. So I'm just creating bins here, and we would measure the frequency. So how many times does a number between 0 and 1.99 show up? Okay. Well, if I count, I've got the 1, the 0, and all of these 1s, and the 0, I've got 7 of these. And if I count the 2 to the 2s and the 3s, I have a total of 5. And the 4s and the 5s, I have a total of 2. All right. Is the creation of a binned frequency table okay? Okay. And so you could define the bins to be any size you want. You know, if I made these any wider, like 0 to 4, it would pretty much cover almost the entire data table. And so in this case, you know, I'm now reduced to just 3 bins, and so my histogram would start at 0, and you draw the edges of each bar to basically the left side of the bin, okay? So I would go 0, 2, 4, and then the next bin would start at 6, and so I would go to 6, and then I draw my vertical axis. And what do I have? And so then I would draw a bar the first bar goes from 0 to 1.99, or basically up to 2, and it's 7 units high. The next bar goes from 2 to 3.99, or 4, and it's 5 units high, and the last one is 2 units high. Okay? And so again, this bin frequency table turns into this histogram. And all we're doing is we're just creating bins to count up our numbers. Okay? Again, we probably wouldn't create a bin frequency table for a small data set with only 14 units, but it's quite useful if you have lots and lots of data, you know, hundreds of data points and things like that. And maybe if you're dealing with heights or weights, okay? You know, if we asked every single student here what was your weight, or we put you on a scale and we measured your weight, okay, if we had an accurate scale, someone might weigh 132.6 pounds and someone might weigh 132.8 pounds. Now, should those two people, they have different weights, and our graphic display could be set up so that they each get their own bin, or we can bin them together, and we can say everybody between 130 and 134.99 pounds will be in this bin, and then everybody from 135 to 139.99 is in this bin, and things like that. And so for probably something like weight, it makes sense to create bins. Okay, so example, you know, if we measure weight, you know, people can weigh 132.6 or 132.8, okay? These are different weights. But they probably do not need their own bars in a histogram. I see your question. I'll get to you in a second. Okay, it makes more sense to make bins such as 130 to 134.99, 135 to 139.99, 140 to 144.99, etc., etc. Okay, we had a question.
Do the bins always have to be relative to one another? For example, that from 130 to 134.99, you added 4.99. Could you have bins that go, say, for example, 135 to 145.99?
Yeah, that's fine.
Yeah.
Yeah. You can create a bin of any width. Okay. So if I wanted to go from 130 to 139, or 135 to 144.99, or whatever, that's fine. You just make sure all of your bins are the same width. Okay.
Okay, that's awesome.
Yeah, all bins should be the same width, but you can make your bins however wide as necessary. Okay. Is this okay?
Yes.
Great. Thank you for saying yes. That's. Sometimes I feel like I'm just talking to myself. Yes. Go back. Absolutely. It's a little awkward seeing yourself on the screen here, gotta say. But
You can't minimize it?
you know, I'm putting it there so in the screen recording, my face is there, because I learned, I don't know, I read up on screencasting and things like that. If you watch like people play video games on Twitch, which probably maybe 3 of you do, or I don't know, whatever. If you do, they all stick their face in their screencasts because apparently it engages people a little bit better to see a face rather than just statistical things. I know, I would be fascinated just enough seeing numbers and charts, but perhaps my beautiful little face will improve your learning experience. I have no idea what's going on, okay? That wasn't a joke, you guys. Okay. All right, let's go on. Well, let's make a stem plot. And a stem plot basically just turns numbers into the histogram itself, okay? So let's say we gathered people's ages, or maybe weights, okay? So let's say we gathered information on weights, okay? And I'm just gonna do like 10 numbers, and let's just say the weights are 132, 145, 156, 137, 160, 112, and 210, and 180, and these are not good. Let me just change these numbers. 217 and 148, 143. Okay. Okay, so let's say for a stem plot, you're basically creating bins, but they're all kind of like 10-unit bins, okay? So you could imagine we're going to create a bunch of bins, and the bins go like, 110 to 119, 120 to 129, 130 to 139, et cetera, et cetera, et cetera, okay? Or 119.99 or whatever, okay? Essentially, we're going to, here, let me just continue this on, 140 to 149, okay? And essentially, we are doing this, and if we look at the 110 to 119, we got one person there. And if we look at 120 to 129, we have no one. And 130 to 139, I've got 2 people. And 140 to 149, I've got 1, 2, 3 people, okay? And the data goes on. Is that okay? Okay, so essentially with a stem plot, you're doing the same thing, except the bins you represent in this slightly odd fashion, okay? You draw, the 110 to 119 bin is represented with an 11. You take the first 2 digits in this case, and then the next bin is represented with a 12, and the next bin is represented with a 13, and the next bin is represented with a 14, okay? And then we say, okay, well, the one person who's in the 110 to 119 bin, the last digit is a 2, so we put a 2 over there, okay? There's nobody who weighs between 120 and 129 pounds in our data, and so we don't put any numbers there. We don't put a 0, we don't put anything there. For the 130s, I've got 2 people. I've got someone who weighs 132 and someone who weighs 137, okay? And so I'm going to put a 2 here, and I'm going to put a 7 here, okay? So this 2 represents 132, and this 7 represents 137. Does that make sense?
Yes.
Okay? And then for the 140s, I've got a 145, a 148, and a 143. So we should put these in order. So it's going to go 143, 145, 148. And we just create our stem plot this way. So I would continue on with the 150s, 160s, 170s, 180s, 190s, 200, and 210s. And this goes on, and so I just go until I check off all of my data points. So at 156, I have someone right there. 160, I've got a person. And then I have someone who weighs 217. And that person shows up down here. Okay, so again, For all of these other groups where nobody appears in our data set, you just leave it blank, and you end up getting something like this. Okay, we have 2 questions, so the one in front first.
Sorry, do you just always cut off the last number, or?
I guess at this point in the course, I'm just going to say yes, but so generally, the bins are going to the stems will be up to the tens place, and the leaf, the part that goes to the right of the line, will be the ones place. But there's no rule against that. That requires that you can do something like the left side will be the hundreds place, and the right side is the tens place, or something along those lines. Generally, we actually don't create stem plots very often in real life. They appear in lots of statistics textbooks, but they rarely appear in newspapers, okay? Histograms, on the other hand, do make their appearances in newspapers, and they are worth understanding. And in fact, if we were to create a stem plot, a histogram, it would look very similar to this stem plot. And if I can illustrate this, maybe I can take this, copy it, and oops, that's not what I wanted to do. You can imagine I just rotate this onto its side like this, okay? And now we have something that kind of looks like a histogram, okay? And you can just imagine I'm drawing little bars. I've got one person here, and so I get a unit that's one bar high, and this one is 3 units high, and that one's 2, and et cetera, et cetera. And now suddenly I have something that looks like a histogram, okay? And essentially a stem plot and a histogram are representing pretty much the same thing, except with stem plots you're kind of required to make these 10-unit bins, okay? Like the 110s and the 120s and the 130s. I mean, I guess you can make other kinds, but generally those are the ones you see most often. Okay, stem plots. We good there? Great. Thank you. Okay, so you can imagine us making a bunch of histograms, okay? And so maybe if I look at a bunch of people's height data, I might get a histogram that looks something I hate this sticky keys thing. How do you make that go away forever? All right. That's what I thought. Okay. All this effort and it looks like crap. So you can imagine a histogram that looks something like this. So that was a lot of work. I'm going to just say, let's say my histogram looks like this instead, okay? And we can represent kind of histograms just with these curves. And just keep in mind that when you see a curve like this, imagine we've got histograms. And I'm leaving something very important off of the histogram. And what am I leaving off? I said every graphic display for a numeric variable has a number line, right? So along here I should have a number line of some kind. And so maybe for height data, I don't know, this is men and women combined, and so we've got 60, 67 and 68, 69, 70, et cetera, et cetera, et cetera. You can imagine a bunch of numbers along this line. And so we would have the same type of thing along here, also numbers, et cetera, et cetera, et cetera, in both directions. Okay? And so when you see a curve like this, remember there is an underlying histogram. And what's beneath the histogram? What is the histogram summarizing itself? The histogram summarizes numeric data, okay? And the histogram summarizes numeric data. Okay, so if this is my histogram and I've got this bar which is centered, which goes from 67 to 68, and let's say, so this one's 71, 72, 73, 74. Okay, so here's a bar at 74, and here's a bar at 68, or 67. What does our histogram tell us about the data points that have values of 67 versus those values that have values at 74? Okay, so what can we say about 67?
More frequent.
67 is more frequent. And 74 is less frequent, okay? So it is not that 67 has a higher value than 74. That's wrong, okay? 74 is a bigger number than 67, so we would never say that 67 has a higher value than 74. But we could say 67 has a higher frequency or is more frequent, okay? And that, if we look at the grand scheme of things, there are probably more people who are around 67 inches tall, so that's 5'7", than there are people who are 74 inches tall, okay, which would be 6'2". Okay, so, you know, 5'7", you've got women who are taller than average and men who are a little bit shorter than average. You've got a good number there. 74, generally you're only going to have men who are taller than average, okay, or some very, very tall women, okay. It's you could have that, but overall these would be less frequent, and this is not a very accurate histogram, so it's probably not as much of a discrepancy as we see in this histogram, but from this histogram we can see that 67 is more frequent than 74, okay. So make sure you're using the words things like frequency and not talking about the value of 67 itself. Okay, so we can talk about the shape of the histogram, and so in this case the shape would be described as unimodal. There are two words that we're going to use for our description of shape: unimodal and symmetric. So when talking about shape, you want to mention two things. Okay, one is the number of peaks, and the other is the symmetry or skewness. Symmetry or skew. So in this case we are unimodal. Unimodal means one peak, and symmetric means symmetric, okay? You guys learned about symmetry, right? You can put a mirror down the middle and it looks the same on both sides. When we're talking about symmetry for numeric data in histograms, what that means is that imagine the middle. So I'm going to draw a line down the middle. So if this line represents the middle, then that means values that are above the middle, okay? So when we go way out here, values above the middle, and when we go in the opposite direction to values below the middle. They occur with about the same frequency. Okay, so if we look at, you know, here we're maybe 6 units above the middle. If I go 6 units below the middle, I should see these values. with about the same frequency. So 6 units above, 6 units below, they should occur with about the same frequency. That's what it means to be symmetric. These values with the same frequency. Okay. Is that okay? Question?
Can you explain the frequency?
The frequency thing? Okay, so here's a bar at 67. This bar is tall. Tall bars mean that value appears frequently. Short bars indicate that this value appears infrequently. Okay, so let's just try another example. Can I go to the next slide or next page? So let's say we're going to let's make another histogram here, or not a histogram, but just a curve like this. Okay. Looks something like this. Okay. You can imagine the underlying histogram looking something, and my histogram is going to look terrible. I'm just gonna forego the straight line assist. Yeah, something's going on here. Okay. All right. So this is the underlying histogram, something that looks like this. Okay. This could be something like number of siblings. Right? If we ask how many siblings do you have, it's probably much more common to have 0, 1, or 2 than it is to have 6 or 7 siblings. Okay? And so this would be, 0, 1, 2, 3. These are probably going to be much more common, okay? These lower values in terms of number of siblings, at least in the United States. How many siblings do you have? A lot of people are going to say, I've got 1 or 2. And maybe not as many with 0, but that's going to be more common than people who are saying, I've got 8 siblings or 10 siblings or something like that, right? There are families with 10 children, but not very many, okay? So if we ask the number of siblings that you have, it's gonna, we're gonna see something like this, okay? So this shape, how many peaks do we have here? 1 peak, okay? There's only 1 hill, so it's still unimodal, but it's not symmetric. It is skewed to the right, or right skewed. Okay, and if you need to, if you need help remembering, just imagine this being a dagger, and you're going to stab someone. Okay, which side would you use for the stabbing, or the skewering? Or maybe that's too violent. Okay. We're gonna make shish kebabs here, and we're gonna put pieces of meat. Okay, the side that's gonna skewer the meat is the right side. Okay, use the right for the skewering. Skewer. Okay. All right, so challenge of the day, not really. What do you think this is called? Skew left. All right, you guys are brilliant. All right. Skew left over here, skew right. Okay, what does it mean to be skewed right? Well, imagine drawing a line somewhere around the middle being, if you had to color this shape in half, or color it, so that half the paint is on one side and half the paint is on the other. Maybe, I don't know, something like this. Does that seem reasonable for about half the areas on the left and half the areas on the right? So this might be our notion of what is the middle, okay? It's not the middle of the number line, so it's not, the maximum, biggest number is 11 and the smallest is 0. We're not going at, 5.5. We're going somewhere where, half of the data is to the right and half is to the left, okay? So if we can go way above the middle, So in this case, let's say our middle is 3. If we go way above, we can go 8 units above 3, up to 11. And are there a lot of families with 11 siblings or 11 children? No, not a lot. But if we go 8 to the left, where would we end up? -5, right? If I tried to go 8 to the left, I would end up at -5. Is it possible to have -5 siblings? No, it's impossible, okay? So skew right means you can have values much larger than the middle, but it is not possible to have values much smaller. Okay? And just the opposite applies for skewed left. You can have values much smaller, but it's not possible to have values much larger than the middle. Okay. What does it mean to be at the peak? It means that these values, whatever's right here, these are the most common, okay? So the peak represents the most common value. Most common values. Is that good? All right. So far when we've talked about shape, we've got a question. Yes. Uh-huh. So just imagine trying to, I don't know, paint this thing, okay? Where would I use half of my paint? Are you saying that the line should be over more to the left or to the right? To the right? Okay, so if I say, you know, let's say, where would you say I should draw it? Somewhere over here? Okay. So I would say, you know, if I were to try to paint this, okay, how much paint would I use covering this area? Just that much, okay? And if I, you know, paint the other side, I feel like I'm using way more paint. Okay? And so what I'm looking for is a spot where about half of the paint goes to the left of the line, okay? And so this, you know, I'm just eyeballing it, but it seems like the amount of paint I would use to paint the left to the left of the 3 is about the same amount of paint as I would use to the right of the 3. And I would say if I moved that line over to the right, I would use much less paint on the right side as I would on the left side. Is that okay visually for you? Yes. Okay, so when we're talking about the middle, and we're going to talk about the mean and the median and in terms of ideas for the middle. But the middle can be thought of as, for one way to think about the middle is, you know, where would you use half of your paint, okay? At what position would you use half of your paint, okay? And that's a good way to get an idea of the middle. The other way is, you know, if this were on a plank, where would I put the little seesaw fulcrum so it stays balanced? That's another notion of middle, okay? All right, I'm going to go to the next thing. All right, so when I said we're talking about shape, there's always two things. And so one thing was we talked about symmetry. and we have symmetric, skew left, and skew right. Okay. And if something doesn't really fit symmetric, skew left, or skew right, you can also say what would we say? Okay, symmetry hard to classify. Yes.
What do you call it if they have more than one peak?
Yeah, so that's the other side I'm going to talk about. Okay, so when we're talking about, so there's two parts. We always want to discuss the symmetry and the number of peaks. Okay, and so for number of peaks, we've got unimodal for one peak. For two peaks, we've got bimodal. And for 3 peaks or more, we generally just say multimodal. Okay, we could say trimodal, but it's less common. Okay, you've got primary and secondary. Technically, you could say tertiary or quaternary, but who uses those words, right? So again, we got unimodal and bimodal, and then beyond that, we generally just say multimodal. So we've already seen unimodal ones where it's like this is unimodal, okay? And bimodal will look something like this, and multimodal could be anything like whatever, okay? A bunch of hills. Okay, so what is something that's bimodal? Okay, let me just do an example of a bimodal distribution. Okay, so here's a bimodal distribution. And if I had to describe the symmetry, I would say it's close to symmetric, okay? And this could be, all right, so what kind of variable are we dealing with here? Yes, question.
Wait, what are those 3 words? What do they say?
Unimodal, bimodal, and multimodal. Here, I'll print it nice and neatly, all right? U-N-I-M-O. Oh, man, I'm trying to write clearly, and it's, like, still terrible. All right. Bimodal and... There we go. Is that better? Maybe. Okay, and this is like gibberish over here. Bimodal distribution close to being symmetric. Okay. Now, what kind of data are we dealing with here when we got a bimodal distribution? So, numeric or categorical? Numeric data, okay? Whenever we're talking about shapes of distributions and all of this stuff, histograms and these curves, it's always going to be numeric data. Okay? So that means down here I've got what? I've got numbers. And so over here I have high values or low values? Low values. And over here I've got high values. So in this case, an example of a numeric variable that has a bimodal distribution could be testosterone levels. Okay? So if you go to the doctor, you could spit in a cup and they can measure your testosterone level. All right? And they'll say, you've got this much testosterone, 130 points. 72 points, whatever, okay? 285 points or whatever. You know, they're measured in something, it's like micrograms per deciliter, some quantity, and I'm not sure exactly how it works, but you get a number, okay, telling you how much testosterone you have, okay? And so, you know, if you're a teenage boy, your testosterone levels are like crazy high because the changes your body's going through and all of this. But let's just say we're dealing with adults, okay? And everybody produces testosterone, okay? Or you should, unless you've got a medical medical thing going on. Everybody produces some testosterone. In general, okay, men produce more testosterone than women, okay? Some men, so this peak over here would represent most likely testosterone levels for men. Some men produce more testosterone than other men. Other men produce less testosterone than others, okay? And if we look at, and this peak would represent probably common testosterone values for women. Some women produce more testosterone than other women. Other women produce less testosterone than others, okay? But in general, even a woman who produces lots of testosterone generally produces less testosterone than a man who is comparatively low testosterone something, okay? So even a man who produces less testosterone than his peers generally will produce more than a woman who produces a lot for her peers, compared to her peers. And so you'll see this kind of bimodal distribution, okay? So this might be like the, quote, average male testosterone level. And over here would be kind of the, quote, unquote, average female testosterone level. Okay, so I'm going to just draw a little, so this will be a male with high testosterone. Testosterone, whatever, okay. And over here, this will be male with low testosterone. And over here, female with high, and down here, female with low. Okay, so is this picture okay?
Yeah.
Everybody can kind of imagine how we might end up with a bimodal distribution here for something like testosterone levels. Did any of you listen to This American Life? No? Okay. It's a radio show. They did a show where everybody had their testosterone levels measured, and it was very interesting and kind of funny. Okay, but whatever. This American Life, you can look it up.
Why was it funny?
I don't know. Testosterone's a funny level subject. Okay. thisamericanlife.org. The shows are about an hour long. You can listen to the podcast that way. Okay. All right, is that okay? So we've got histograms to display numeric data, and we can describe the shape of histograms using these words. Talking about the symmetry, talking about the number of peaks. Oh, it's 8:30. Okay, let's take a 10-minute break. We'll come back and we'll do chapter